In this video, we're going to see a few examples of linear programming problems. Even if it's not really the focus of this course to see real-world examples of optimization problems and model them as linear programming problems, I still want to show you a few examples here. We start with a production problem, which will be really straightforward to write down as a linear programming problem. What we're going to do in all this example is first we state the problem in words and then we write it down as a linear programming problem. So in our production problem, we have n different goods and m different materials. We also know exactly the available amount of every material that we have, and this is encoded in the number bi for I that goes from 1 to m. Therefore, B1 will be the available amount of the first material, B2 of the second material, and so on and so forth. Next, we know the connection between the goods and the materials. Namely, for every good, we know exactly the amount of material required to produce such a good. In order to produce the jth good, we need aij units of the material I. So also all these aij form the data that is given to us in this problem. The last amount of data that we need is the revenue. So we know that selling a unit of the good j will result in a revenue of cj. The question is, what is the optimal strategy in producing these goods? Namely, how much of each good should we produce in order to maximize the total revenue? Now, every time we have an optimization problem stated in words, the first thing that we should do in order to translate it into a linear programming problem is to write down the decision variables. So the decision variables normally are exactly the things you should decide in your problem. In our case, we need to decide how much of each good we should produce, and so we introduce the decision variable xj that represents exactly the amount of the jth good that we produce. And at this point, writing down the formulation is straightforward. The first thing we should look at is the objective function. So we want to maximize the total revenue. Now for the good j, the revenue is cj times xj. So the revenue per unit times the units produced. And so of course we sum over all the goods. Then what are our constraints? Well, first, we know that we can produce only non-negative quantities, so we have xj greater than or equal to 0 for every j, and the only remaining constraints regards the available amount of the materials. In fact, for every material, we cannot use more than bi units of such a material. So, how many units of material I are used in our production? Well, this is the sum of how much of this material is used to produce each good. So we sum over all the goods, and each good requires exactly aij times xj unit of this material. So in total, this is our linear programming problem. We maximize our objective function subject to the constraints. As you can see, all the functions that we've written here are linear, and so this is a linear programming problem. In the next example, we're going to see the multi-period planning of electric power capacity. This optimization problem will be definitely more complicated to state than the previous one, but I promise it's going to still fit in just one slide. So our task here is to plan the electricity capacity for the next capital T years, and these years will be denoted by year 1, year 2, until year capital T. We already know the demand for electricity that we are required to meet at every year. And this is encoded in the number dt. So dt represents exactly the demand in megawatts during year t. And again, t ranges from 1 to capital T. So the demand in year 1 will be d1, in year 2 is d2, and so on and so forth until d capital T. In order to meet such a demand, we already have some power plants, and these are all oil power plants. We also know how many megawatts these oil plants will produce in each year, and this is encoded in ET. So in year T, our oil plants will produce ET megawatts for every T that goes from 1 to capital T. In general, this capacity will not be sufficient to meet the demand. So what can we do about it? Well, we can build new power plants, and these can be either coal plants or nuclear plants. Building these plants has, of course, different costs. And also here, we know exactly how much it costs to build coal plants or nuclear plants. So the cost is expressed in cost per megawatt that such a plant will produce. In particular, the cost per megawatt for coal plants is CT, and for nuclear plants is NT. Note that also here we have a subscript T, and this is because these costs are not the same every year. Now the difference in coal and nuclear plants is not just in the cost per megawatt in constructing such a plant, but it also lies in how long this megawatt will be available. So essentially how long these plants will last. And we already know that coal plants last for 20 years while nuclear plants last for only 15 years. Therefore, even though, let's say, N1 could be, for example, smaller than C1, then it's not necessarily true that it's better for us to build nuclear plants only in year 1, because the nuclear plants produced in year 1 will stop working in year 15, while the coal plants will work until year 20. To conclude the description of this optimization problem, there's only one more constraint that we have. In fact, for political reason, we know that no more than 20% of the total capacity in each year should ever be nuclear. Of course, our task is to find a least cost capacity extension plan which must meet the demands. Once again, the very first thing to do is to decide which are the decision variables. Also in this problem, we're gonna use the most natural ones. We have to decide every year the amount of coal and nuclear capacity to bring online in such a year, and this will be denoted by xt for the coal and yt for nuclear. At this point, we can easily write down the objective function. So remember, we want to minimize the total cost. Now, what is the cost in year t? Well, we need to pay ct times xt to bring online all the coal capacity and nt yt to bring online all the nuclear capacity. And of course, we need to sum over all t's. At this point, before getting to the constraints, I want to introduce some more decision variables. I'm going to talk more about these decision variables once we have fully written down our linear programming problem. What you need to know right now is that it's not really necessary to introduce these auxiliary variables, but it will make our life easier. So my additional decision variables are Wt and Zt, and they represent the total coal and nuclear capacity available in the year t. Our first constraints then will be the ones that link our new additional variables with the original variables. So Wt is the total coal capacity available in year t. And so how can it be written in terms of the x variables? Well, Wt will be equal to xt, which is the coal capacity which we just brought online in the same year. But remember, the coal plants last for a total number of 20 years. Therefore, in year t, we also have available the capacity which was brought online 1 year ago, 2 years ago, and so on and so forth until 19 years ago. So for a total of the last 20 years. This is why Wt can then be written as the sum of xs for s that ranges from the max of 1 t minus 19 and t. I'm sure at this point you're wondering why there is this strange max. It would have been kind of more intuitive to simply have s that ranges from t minus 19 until t, and this matches exactly the discussion that we just had. However, remember that our time horizon starts only in year 1, therefore we don't want to consider any xs with s equal to 0, minus 1, minus 2, minus 3, because these decision variables don't exist and also don't make sense. In a sense, it's just like having all of them being equal to 0, since there was no coal plants, before year 1 because we only had oil plants. So essentially, when we sum the last 20 XS for the last 20 years, we can just stop at 1 in case t minus 19 is a negative number or 0. For example, these constraints for t equal to 3 will be simply W3 equal to x3 plus x2 plus x1. Now, similarly, nuclear plants last for 15 years, and so we can write Zt equals the sum of the ys for s that goes from max 1 t minus 14 until t. And once again, except for this technical case where the 1 comes into play, in total, I'm summing the very last 15 variables ys. And this is because nuclear plants last for only 15 years. So now we can get back to the constraints of the problem. And now that we have introduced our new variables Wt and Zt, it will be very simple to write them down. So the first constraint says that the available capacity must meet the forecasted demand. Therefore, for every year, t that ranges from 1 to capital T, the demand is dt, and the available capacity is the available capacity in oil plants plus nuclear plants plus coal plants, and so we can simply write Wt plus Zt plus Et greater than or equal to dt. Another constraint is that no more than 20% of the total capacity should ever be nuclear. In order to write this constraint, for every year from 1 to capital T, we simply write the ratio of the total nuclear capacity over the total capacity. So this is Zt over Wt plus Zt plus Et, and this must be at most 0.2 because it's 20%. Note that this inequality is not linear because the function on the left hand is not a linear inequality. However, it can be easily transformed into a linear constraint by multiplying both the right hand and left hand by the denominator Wt plus Zt plus Et. In this way, the denominator will vanish on the left hand and it will be multiplied by 0.2 on the right hand. Now Zt will appear both on the left hand and on the right hand, so part of it can be simplified, and what you obtain is this inequality. 0.8 Zt minus 0.2 Wt is less than or equal to 0.2 Et. You might be wondering why I suddenly brought the 0.2 Et on the right hand of this inequality, and the reason is that it is a standard notation to have all the variables on the left hand and all the numbers on the right hand. And remember that Zt and Wt are decision variables. These are things we will have to decide. On the other hand, Et is data, is a specific number for every t that is given in input. At this point, we can write down the full linear programming formulation. We have to minimize our objective function subject to all the constraints we have so far written. The first one is the equality constraints that comes from the definition of Wt in terms of the x. The second comes from the definition of Zt in terms of the y's. Then we have the two inequalities we have just written down, and we shouldn't forget that all our decision variables should be non-negative because we can only bring online a non-negative number of megawatts. At this point, as promised, I want to spend a couple of minutes regarding the additional variables that we defined. So the reason is that I'm sure you're wondering, well, what if I didn't know I should introduce those type of variables? In fact, I kind of defined them a little bit out of the hat. Well, now, if you think about it a little bit more deeply, they're not really out of the hat too much because when we wrote down the main inequalities of the problem, which are these two over here, these quantities are those that appear exactly in these inequalities. And so it kind of makes sense to think about those first before writing down these inequalities. In any case, even if you didn't think about this, it doesn't really matter because we can at this point write down another linear programming problem that doesn't have these new variables and that is equivalent to this one. How can we do that? Well, look, Wt is equal to this sum because of this constraint, and Zt is equal to this sum because of this constraint. Well, that's obvious, that's exactly how we define them. So now what we can do is simply trash these equality constraints and then replace Wt and Zt with the corresponding sum in the remaining inequalities. So then we will no longer have wt here and no longer have zt here, and instead we'll have a sum of x and here a sum of y. Similarly, also here we only will have y and x variables, and so in our formulation these variables will completely disappear and end up with a linear programming problem that only contains the variables x and y's. The last thing I want to discuss is what about non-negativity. So here we quickly wrote that all our decision variables should be non-negative. However, if you think a little bit more deeply about this, we could definitely avoid writing wt and zt over here, because what is really important is that x and y's are greater than or equal to 0. Then the non-negativity of w and z immediately follows from these equality constraints. In fact, each wt is the sum of a bunch of x variables, and since they're all non-negative, then so will be wt as well, and similarly for zt. And this concludes our example on multi-period planning of electric power capacity. The next example of a linear programming problem that we're going to see is a scheduling problem. In this example, we have a hospital that needs to make a weekly night shift schedule for its nurses. And we know exactly for every night of the week what is the demand for nurses. And this is encoded in this quantity dj for j that goes from 1 to 7. So in day 1, the demand is d1, day 2 is d2, and so on and so forth over the week. And the next week, everything repeats with the same d1, d2, d3 until d7, and so on and so forth. An important constraint in this problem is that every nurse needs to work for exactly 5 days in a row on the night shift. And of course, the question is to find the minimal number of nurses the hospital needs to hire. As always, the first thing to do is to decide what are the decision variables. Probably the most intuitive way of defining decision variables is to have a variable x1, x2, x3 until x7, so 7 variables, and each one should represent how many nurses work in that specific day. I encourage you to try to write down a linear programming problem that uses these decision variables. You will soon realize that it's very difficult, if not impossible, to write down the constraint that every nurse should be working 5 days in a row. Instead, we define a different decision variable xj, which represents instead the number of nurses that start their week on day j. So they're going to be working on day j, j plus 1, j plus 2, j plus 3, and j plus 4. Of course, modulo 7. So at this point, we can immediately write the formulation. So we want to hire the minimum possible amount of nurses. Every nurse must start in a specific day, therefore the total number of nurses hired is exactly x1 plus x2 plus x3 until plus x7. So let's now talk about the constraints. We need to write down that in every day of the week we have enough nurses. Let's start, for example, with day 7. So we need at least D7 nurses working on that day. And so which nurses will be working in that day or, well, in that night? Well, those that start their week on the same day, plus those that started the week 1 day before, 2 days before, 3 days before, and 4 days before. Now, the ones that started 5 days before, of course, they will not be working on the day 7 because they have completed their shift on the day 6. Therefore, the constraint corresponding to day 7 is this one, x3 plus x4 plus x5 plus x6 plus x7 greater than or equal to d7. Now, similarly, you can obtain all other days. For example, what are the nurses that will be working on day 1? Well, they will be the nurses that started on the same day, so x1, plus those that started in the previous day, which is day 7, plus day 6, plus day 5, plus day 4 of the week. Next, the number of nurses hired in each day must be for sure greater than or equal to 0, but it also must be an integer number. We definitely cannot hire 0.3 nurses on a specific day. It must be an integer. Therefore, this problem is not a linear programming problem. It's very similar to a linear programming problem. The only problematic constraint that is not allowed in linear programming is exactly this integrality constraint. Due to this integrality constraint, this is called an integer linear programming problem. These problems are much more difficult to solve than linear programming problem, both from a theoretical perspective and from a computational perspective. As you can imagine, integrality constraints often arise in real-world problems, and there are several techniques to deal with these problems. We're not going to talk about it in this course, but we have a full course devoted to this type of optimization problem, which is the course 728, Integer Optimization. In any case, I still want to make a couple of interesting observations about this integer linear programming problem that we have just seen without the need for you to take 728. The most natural thing that we can do in this integer linear programming problem is just to ignore the integrality constraints. Well, why? Because in this way we obtain a linear programming problem, and this is called the LP relaxation of the original integer linear programming problem. So here is our problem, and as you can see, we just trashed these integrality constraints. Now, the first observation that we can make is that the optimal cost of the linear programming problem will be less than or equal to the optimal cost of the original problem. The reason is that any feasible point for the integer linear programming problem, of course, will be also feasible for the linear programming problem because it just has fewer constraints. Therefore, the linear programming problem has a feasible region that is larger than that of the original integer programming problem. Since we're minimizing the same objective function, then the optimal cost of the linear programming problem can only become smaller. The next observation is that if it just so happens that the optimal solution to the LP relaxation is integer, then it is also an optimal solution to the original problem. So why is this true? Let's call x star the optimal solution to the LP. Since x star is feasible to the LP and is also integer, it is feasible to the integer linear programming problem. But then why is it optimal? Well, because it's already the best solution among all the feasible solutions to the LP. Therefore, it must be the best solution also among the smaller set of the feasible solutions to the integer linear programming problem. So this gives us a nice way to try to solve integer linear programming problems, namely trash the integrality constraint, solve the linear programming problem. You just might be lucky and obtain an integral solution, in which case you have completely solved your integer linear programming problem. Of course, in general, you will not be that lucky, and this is where things become harder. However, we can make a very simple observation that doesn't work for any integer linear programming problem, but it works for the example we are talking about. Namely, what you could do is obtain a feasible solution to the original problem by rounding every xj that you obtained upwards. For sure, you obtain a feasible solution to the original problem because by rounding you obtain integer variables, so you satisfy the integrality constraint, and you will still satisfy all the inequality constraints because you're just making larger the left-hand side. Of course, this solution is not necessarily optimal, and it's also really hard to say how good this solution is. So it's definitely not a satisfactory way to deal with our scheduling problem, but at least it's a way. If you want to know more about how to deal with integer programming problem, you should of course take 728. The next example is about choosing paths in a communication network. In this problem, a communication network is given to us, and the communication network looks something like this. The way you should think about this is that you have a bunch of, let's say, offices of your company, and these are formally called the nodes of the communication network. Now, in this picture, these are the circles with the number inside. Then you have a number of communication links that connect your nodes. Now in these pictures, these are the arrows. For example, here we have an arrow from 1 to 4, and this represents the fact that you can transmit data from your node 1 to your node 4. Formally, we're going to denote our communication network by G, which is a pair, NA, where N is the set of nodes and A is the set of communication links. To denote a link, we're going to use this notation. IJ in parentheses means that this is the link starting in I and ending in J. In this problem, then, we're given a communication network, but this is not the only data that we're given. In fact, for every link ij, we also are given a number uij that represents the maximum amount of bits per second that can be sent along such a link. Moreover, in order to send this amount of data, we have to pay, and we're given for every link Cij the cost per bit transmitted along such a link, and this is encoded in Cij. Then we're given values bkl for every pair kl of different nodes. And bkl represents the amount of data that is generated at node k and that should be sent to node L. So how can we transmit the data? Well, we can either transmit it directly from k to L along a direct link kl, as long, of course, as it exists, or we can instead use a sequence of links that starts in k and ends in L. Moreover, the data from K to L doesn't need to travel along the same path, but it can be split and be transmitted along different paths. What is then our objective? As you can imagine, it is to send all the data that is generated in our communication network, while at the same time minimizing the total cost. As always, to model this problem as a linear programming problem, we first have to decide our decision variables. For this problem, our decision variables are x, ij, kl. They indicate the amount of data that traverses the link ij that is generated in node k and is destined to node L. Once we have defined these decision variables, it's really easy to write down the objective function as always so far. So how much do we have to pay to send the data xijkl? Well, this is data that traverses the link ij, and the cost per bit in such a link is given by Cij. Therefore, it's going to be Cij times xijkl. Of course, we now need to sum over all links ij and over all origins and over all destinations. And this gives us our objective function to be minimized. Let's now discuss the constraints. Our first constraint is the easiest. In fact, we can only send a non-negative amount of data along every link. Therefore, we have non-negativity on all our variables. Then we have the capacity constraints. Remember that for every link ij, no more than uij bits can be sent per second. Therefore, we only need to compute how many bits per second we are sending along such a link. In order to do so, we take our xij, kl, and sum over all k and over all l. And this inequality holds for every link ij. We are only left with one type of constraints to write down, and these are constraints that are very common in this type of network problems, and they're called flow conservation constraints. Think about the data generated in K with destination L. In this problem, we have to decide how this data flows essentially from K to L. So essentially what we need to do in these constraints is guarantee that the only type of data with origin K and destination L is generated in K and is absorbed essentially in L, and along any other node of the network, no such data is ever generated or absorbed. In order to write down these inequalities, we need to write down what is called the net flow at every node I, and this will be denoted by BI-KL. This represents this quantity that we just discussed, namely the amount of data from K to L that is generated in I. Formally, this is the flow that exits I minus the flow that enters I. So how is this quantity defined? Well, it is of course 0 if I is different from k or L. On the other hand, if it is equal to k, then BKL is generated in such a node, and if I is equal to L, then BKL is absorbed in that node, and therefore we're going to write minus BKL. We're now ready to write the flow conservation constraint. Essentially, to do so, we're gonna have to write the same net flow using our variables x instead. So the definition of net flow, once again, is the flow that exits I minus the flow that enters I. So let's start to write down the flow that exits I. So if it exits I, it will correspond to a link ij in A. And so everything we need to do is to sum over all these links, ij for any j, the quantity xij kl. Then from this quantity we need to remove the flow that enters I, and this is very similar. However, such a flow will enter through a link of the type ji for any possible j, and we're summing xji kl. In this way, we have written our net flow at node I with respect to the flow with origin k and destination L. Earlier on, we wrote down the same net flow that we should achieve given the data of the problem, and so we have to enforce equality between these two quantities. How many inequalities do we have? Well, we will have one for every I and for every KL. And that's all. We are ready to write down our full formulation, and I'm just pasting here our objective function together with all the constraints that we have written so far. Now, in the real-world application that we were thinking about in this example, we had a bunch of different, let's say, offices, and we wanted to transmit data among them. Now, of course, there can be many different real-world problems that actually fit the same type of linear programming problem. Another example is whenever you want to transport several different commodities from their origins to their destination through your network. And this problem is known as the multi-commodity flow problem. And every commodity corresponds to the traffic in each origin-destination pair. In a simpler version of this problem, we don't distinguish between different commodities. And this is called the minimum cost network flow problem. In this problem, instead of having all the BKL data in input, we only are given the amount BI for every node. And this represents the external supply or demand at each node I. If BI is positive, then I is called the supply node, and if BI is negative, then it's called the demand node. Then the problem is, of course, to transport the material from the supply nodes to the demand nodes at minimum cost. In turn, the network flow problem contains a bunch of other problems as very special cases. For example, the shortest path problem, which finds the shortest path to go from an origin to a destination point. The maximum flow problem, which is the problem of sending the maximum amount of flow possible, again from an origin node to a destination node. And the assignment problem that finds, for example, the best possible assignment of workers to jobs. Therefore, all these network problems can be solved via a linear programming problem. And they can be solved efficiently in this way. However, it's important to note that these problems have such a special structure and are so important that people have been studying them and developing for them algorithms that work specifically just for one of these problems. Of course, such an algorithm can take advantage of the very special structure of this problem, so in general it will be much faster than solving the problem with linear programming. In UW-Madison, we have a course dedicated to this type of algorithms, and this is our 425 course, Introduction to Combinatorial Optimization. And this is all for this video. In the next video, we're going to look at a class of nonlinear optimization problem that can be formulated as linear programming problems.